Welcome to Calculus 2, Section 1.1, Approximating Area. To begin, we'll look at sigma notation. Here we are, approximating area, sigma notation, and an example. Greek letter capital sigma, index I beginning at 1 up to 3, and ith summand 1 over the index. So this example represents a sum of 3 terms. When the index I is at its first value, I equal 1, we plug that into the form 1 over I. 1 over 1 we know evaluates to 1. As we increment the index, we write down a plus sign and then evaluate 1 over I for the next value of I. Incrementing from 1 to 2, we get that 1 over I becomes 1 over 2. Incrementing one more time brings the index I to 3, which matches the terminating value given at the top. Writing down 3 terms is not very tedious. Writing down 100 terms might become troublesome. And summation notation provides a compact notation for writing down the sum of many, many terms. Note that here our ith term is just the index, in contrast to the previous example where the ith term was 1 over the index. In this example, we're looking at summing up the first 100 positive integers. Let's make a few notes. I is the index of summation. I is a dummy variable. Here we're also using I as the particular value of a sub I. A sub I is the ith summand. Very nice. Okay, let's go over how to read sigma notation. This Greek letter capital sigma is read the sum. You next look directly underneath it for where the index begins. On the screen we have the sum from I equaling 1. Then you look to the top to find where the index I terminates. So on the screen, the sum from I equal 1 to n, and then you look at what the ith summand is. So this whole summation notation is the sum from I equal 1 to n of a sub I. Very nice. Let's do an example. Suppose that the ith summand is base 2 raised to the index I. Then this sigma notation has the index beginning at 3 and ending at n, with ith summand taken to be 2 raised to the index. Let's express this out. Then 2 raised to the index, where does the index begin? In this instance, the index is beginning at 3. So the very first term is 2 to the power 3. Successive terms have the power incremented by 1. And when do we stop? Adding in new terms when the power is equal to the terminating value, n. Very good. So anytime we come upon an assignment, you want to pause the video, work the assignment, and then resume the video. In this instance, it's a review of sigma notation. So use as the ith summand base 2 to the I for the index I running from 3 to 6. Write out that sum in sigma notation, and then come up with the overall sum of that value. Very nice. So we have gone over sigma notation. Next, let's look at properties of this sigma notation. Here on the left, we are looking at the sum from I equal 1 to n of a constant c. We had a nice animation show n copies of c being added together. What's another way to write down c added with itself n times? Well, n times c. This is the first property of summation notation. This sum of a constant added with itself n times is simply the constant times n. Move on to the second property. Let's take again c to be a constant, but a1, a2, an, let that be a sequence of numbers. So each ai is a real number. Let's use summation notation. First, let's multiply each term of this sequence by a constant c. That will produce a new sequence of numbers, exactly n numbers. Let's add all those numbers together. That's represented here on the left-hand side. Explicitly write it out on the right-hand side. And very easily notice that these n terms on the right-hand side all have a common factor of c. Simple algebra tells us that we can factor off that common factor c from these n terms. And then looking at those n terms being added, we know that we have sigma notation to represent that. And what's happened is that this constant c has gone from operating on each single term to now just operating on the entire sum. Another way to state that is that c is able to pull through the operation of summation. Very nice. Let's look at a third property of summation. So here we have constant c again, a first sequence of terms given by ai's, and then a second sequence of n terms given by bi's. The third property is this statement here. Let's look on the left-hand side. And term-wise, ith term from the ai's and ith term from the bi's, let's add corresponding terms together. That'll produce n sums, or if we choose differences, n differences. And then add all those together. this third property is saying that if you change the order to instead adding up all the a's and then adding up all the bi's, and then bring those two sums together, either as a sum or a difference, that these quantities on the left and on the right will agree. Now, because we are dealing with finite number of terms, these statements are rather straightforward. And much later on, you want to keep that in mind, that for the finite case, this is very straightforward. Okay, we have a fourth property. Suppose that we have n terms, a sub I, and we want to add them together. Now, if we pick a value m somewhere between 1 and n, and instead of adding up all n terms, we only add up the first m terms, and then as a separate operation, add up the remaining terms, and then bring these two sums together, that this sum on the right will equal the same thing as having added up all the terms in one go. Again, that should sit very well with you as being obvious. And you want to remember how obvious it is in this case when we apply it to different notation representing areas. All right, so this is a fourth property to the previous three that we had. Very good. All right, another assignment. And this assignment will actually rely on material that we're going to look at in just one second. But the idea is that you want to use the properties of summation and use this 3 plus 4i as the ith summand, where the index first runs from 1 to 100, and then come back and consider what if you had the index run from 5 to 100. And again, you're going to rely on information that we're going to look at next. Okay, so we've gone over the basic notion of sigma notation, 4 different properties for sigma notation, and next we want to come up with formulas for how to evaluate sums and powers of integers. So here are 3 expressions where the ith summand is the index raised to a power. Power 1, power 2, and power 3. And we want to find out a way to evaluate this expression. Let's start with the first one. And let's take as an example a value for n of 100. So here is written out the sum of the first 100 counting numbers. And I've highlighted the very first and the very last. And the very last, remember, is the value for n. And by highlighting them, I'm asking you to sum them together. So 1 plus this value of n will produce 101, or let's say n plus 1. That's using the sum of the first and the last. Let's try the second and second to last. And when we sum the second and second to last term, we again produce n plus 1, 101. And that's the same thing again on the third and third to last. How many opportunities do we have? How many pairings do we have that produce n plus 1? Well, for each term, we have to find its pair. So we're going to take the number of terms and divide that by 2. And that's what we get. So here's our first formula. The sum of the first n integers is n product binomial n plus 1 over 2. Very nice. Write down the second formula for the sum of the first n integers squared is a similar formulation. Have in the numerator n product binomial n plus 1, but here we're going to need a third factor, 2n plus 1, and in the denominator, instead of a 2, we'll have a 6. Very good. For the third summation, it's very much related to the first formula. You take the first formula and you square it. So take n, square it. Take binomial n plus 1, square it. Take denominator 2 and square it. Fantastic. So these are sums and powers of integers, and they help us evaluate change from summation notation into some formula that depends on the terminating value n. Let's do an example. So the n value is 123, and then the ith summand is a binomial raised to the power 2. What we're going to want to do is use some algebra, properties of summation, and then these sums and powers formulas that we just wrote down. Let's start with the algebra. Take the ith summand and multiply it out. 3i times itself is 9i squared. 3i times negative 2 is negative 6i. Double that up to get negative 12i. And negative 2 quantity squared is positive 4. All right, nice scratch work. Go ahead and swap out the binomial squared with this trinomial to get this expression. And this is a typo. That should say, instead of negative 6i, that should say negative 12i. Be corrected in a slide coming up. And what we're going to do next is, we've done algebra. We're now going to use properties of summation. And a property of summation that we can use is this notion of the operation of summation onto a sum or difference of sequences can be distributed. We can distribute summation to the AIs and to the BIs. Let's do that. So distributing the summation onto the 9i squared, distributing summation onto the negative 12i, and distributing summation onto the 4 produces this sum and difference of 3 summations. So that's using this one property of summation. Remember, we had 4 properties. We have 2 more that we can apply. In the first 2 summations, there is a constant times a varying function of I. A property of summation is that that constant can pull through the operation of summation all the way to the front. So in the first 2 sums, we're going to be able to pull out in the first one a 9 and the constant 12 in the second. The third summation is summing up a constant And we know that that can be evaluated as the constant times the number of times it's being added with itself. So if we do that, bring the constants 9 and 12 to the front, and the third summation, we can wholesale evaluate it out. Good. Let's multiply out this product of 4 and 123. And then let's look at these summation. Let's start here. Summation of I. So what is the sum of the first 123 counting numbers? We have a formula for that. We also have a formula for the sum of the first 123 counting numbers squared. So here's that formula. We're going to use it by plugging in for n the value 123. And here's the formula for summing up the first n counting numbers. And again, in this formula, we'll plug in for n the value 123. We go ahead and do that. Here's what we get. Highlighted is our plugging in of n at 123. Fair bit of algebra to do. Once done, produce a value, and that finishes this example where we have employed algebra, properties of notation, properties of summation. There were 4 of them. We employed 3 of them. And then formulas on how to evaluate sums and powers of integers. We employed 2 different formulas. Excellent. All right, here's another assignment, nearly identical to the example that we just finished. But on closer inspection, you see that the power on the binomial was 2 in the example. And here in the assignment, the power is 3. So a fair bit more algebra involved. Otherwise, it's just going back over the example that we did. Good. Let's press on. So that finishes up the first portion, which dealt with sigma notation. For the second portion, our intermediate goal is to come up with a Riemann sum. And our starting point is to write down a definition of a partition. So we have a vocab word, partition. And a partition is going to break up an interval, a closed interval. A partition is this guy, capital P. Looking at capital P, it's being set equal to something. The expression is a paired curly brace expression. Whenever you have paired curly braces, you're denoting a set. You look inside the curly braces and you see xi's. So xi's are notation for points on a number line. Now, how do we want to pick those points so that this P, given as a set of points, partitions a closed interval, a to b? We want to pick these points, there will be n plus 1 of them, such that the very first value that we pick is exactly the left endpoint A. And the very last value that we pick is exactly the right endpoint B. And then that's 2 points, and then you pick n minus 1 points in between. Okay, so this is a partition. Let's bring in a picture. This is just a number line. Let's pick on the number line the value A and the value B, and then denote the closed interval by picking everything in between A and B, inclusive of the A and of the B. So this is representing the closed interval A to B. Next, let's denote the partition of the n plus 1 terms. So here are some tick marks where we are including A and B. And then let's put some notation on these tick marks. The very first tick mark, let's call that x naught, x sub 0, which is A. The next tick mark, x1, second term in the partition, and then x2 and so forth, and ending with the n plus first term, x sub n, taken to be B. And then along the way, pick any term and suppose that that is x sub I, and consider the term immediately preceding it, and that term will have index I minus 1. These two adjacent terms are giving a left and right endpoint to the ith subinterval. Now, as we have it pictured here, each interval is the same width, and each of these intervals of the same width, they total up to n many subintervals. All right, let's go back to this idea that each has its same width and write down another vocab word that when we pick our partition such that the left and right endpoints on all of the subintervals are the same distance, then the partition is regular. Let's read this. A partition is regular if each subinterval x sub I minus 1, comma, x sub I, has the same width delta x, that's the width, that's how far it is from one left endpoint to its adjacent right endpoint. And then what is that width? Well, we know that there are n many subintervals, and we want them all to have the same width. We should look at the total length, b minus a, and divide that by n, the number of subintervals we want to produce. Very good. So we will always choose regular partitions. Nice. Spending a little bit more time here. We have a left endpoint on the ith subinterval. We have a right endpoint on the ith subinterval. The notation is x sub I to represent right endpoints. Take away 1 from the I, and you have a left endpoint. How do we produce those values? Well, if you look at the very first right endpoint, it is exactly delta x away from A. If you look at the second right endpoint, how far away from A is that? 1 copy of delta x, a second copy of delta x. It is 2 copies of delta x away from A. So x sub I, being the right endpoint to the ith subinterval, will be I copies of delta x added to A. For the left endpoint, if you view the left endpoint as a right endpoint of the I minus first subinterval, then you should add I minus 1 many copies of delta x to A in order to get x sub I minus 1. Excellent. So we have left endpoints and right endpoints, and we have convenient ways to express them out. Very good. Okay, so two different intervals, 0 to 1, 2 to 5. For each of these intervals, create a regular partition. And on the unit interval 0 to 1, break up that interval into 4 equal pieces. That'll require choosing 5 points in the interval 0 to 1. For the interval 2 to 5, break it up into 9 equal subintervals by choosing 10 points from the interval 2 to 5. Beautiful. All right, so that is the idea of partition. Let's look at left-endpoint approximations. Okay, we have a partition of A to B, and the animation picked out only left endpoints. X sub n is a right endpoint only, and it's not picked. Above, we have the graph of a function, f of x. And on this partition, we've picked left endpoints. Let's use those left endpoints as inputs to the function f. And then plugging in those left endpoints, we produce outputs, f of a left endpoint. And we're using that to produce a height of a rectangle. Let's go over here and look at the ith rectangle. And on this ith rectangle, its height is the value of the function at the left endpoint of the ith interval. We know how to compute the area of a rectangle, length times width. Length, let's term that as height, and width, let's term that as the base. Then this quantity a sub I, the area of the ith rectangle, is given by height times base. And we know how to produce the height. We evaluate the left endpoint. We evaluate the function at the left endpoint to get the height. As we always take a regular partition, the base on each of these rectangles will all be the same. Our notation for the base is the length of each subinterval, which is delta x. The total length of the interval divided by n. What we're wanting to do in order to approximate area is add up the area of all of these n rectangles. And to add up all of these areas, we need to employ sigma notation. Each area is given in the form of f evaluated at the corresponding left endpoint times the length of the subinterval delta x. So here's the expression for a sub I, and we want that I to run from 1 up to n. Since the height is given by the function at the left endpoint, we're going to term this summation the left endpoint approximation and denote it with capital L sub n, where n is the number of rectangles. Very good. So, use for a function f, the radical function, use for the interval a to b, the closed interval 1 to 2, and go through these 4 steps. Write out what delta x is for an arbitrary n. For that arbitrary n, determine how to express out a left endpoint. Then having that left endpoint, you can evaluate the function at that left endpoint to get a height. And you know that taking the height times the base gives you area. Adding all those up will then give you a left endpoint approximation for an arbitrary n value. And then I'd like you to consider n values of 10, 50, and 100. That's a lot to do by hand, so use a computer to produce these values. Left endpoint approximations, n equal 10, 50, and 100. Beautiful. That's left endpoint approximation. Right endpoint approximation is nearly identical. The only difference being that instead of producing heights with left endpoints, we now use right endpoints. There's the function evaluated at all n right endpoints. And then corresponding rectangles. And note that this function is an increasing function, so that each rectangle protrudes past the graph of the function. Whereas before, using left endpoints, each rectangle was contained within the graph. Okay. So, right endpoint approximation, let's go ahead and write that out, will be denoted R sub n. And it is the sum from I equal 1 to n of the area of the corresponding rectangle, which is a height times base. And for the height, we are evaluating the function at right endpoints. So that's f not at x sub I minus 1, that's f at x sub I. And the base is the same for each. In other words, we're using regular partitions. So this is R sub n. Very good. For this assignment, use the function, linear function, f of x is x. Same interval a to b as 1 to 2. Go ahead and make a sketch of y equal x over the interval 1 to 2. Shade underneath that graph and above the x-axis. And you can use simple geometry to find how much area is underneath that curve. Compute out L4 and R4. And then relate L4 and R4 to the actual area under the curve using inequalities. Fantastic. So now we want to generalize this notion of left and right endpoint approximations into the notion of a Riemann sum. And to kind of motivate that, let's look here that R1 is grossly underestimating. That's this blue shaded box, is grossly underestimating the area under the red curve over the interval 1 to 3. On the other hand, L1 grossly exaggerates, overestimates the area under the curve, this red curve from 1 to 3. So 1 is over, 1 is under. However, if we take the number of rectangles to be larger and larger, that's R1, L1, and then use Ln, where n grows larger and larger, we get better and better approximations of the true area under the curve. Though zooming in, we can see that we don't have exact area, but we have, zooming out, a pretty good approximation. And that approximation on this zoomed out level is going to look equally well by using a left endpoint or a right endpoint. So left endpoint or right endpoint, when the number of rectangles becomes extremely large, they're equally going to produce a good approximation. So the notion of a Riemann sum is to loosen that up even more and say, well, let's produce heights of rectangles by looking at any point in the ith interval. And the notation to represent any point is the asterisk. And this arbitrary term is read x sub I star, or xi star. And using any point in the ith interval to produce heights of rectangles is exactly the defining characteristic for a Riemann sum. Very good. So this is a Riemann sum. All right. With that, then, we're able to make our definition of the area under the curve. And then we'll take a quick look at upper and lower sums. So we've just made a definition of a Riemann sum. Now we're going to make a definition of this phrase, the area under the curve. And this definition is going to hold provided that we have a good function. By that we mean that we're going to assume the function is continuous and non-negative over a closed interval a to b. If we have such a function, then by definition, the area under the curve y equals f of x on this interval a to b is the limit of a Riemann sum. So here is the Riemann sum. We're adding up the area of n rectangles, where the heights of the rectangles are provided by evaluating the function at any term in the ith interval. That's the Riemann sum. Then taking the limit, and here we're taking the limit as n goes to infinity, meaning that we're letting the number of rectangles become infinitely large. Doing so, how is that going to affect the base? Remember, this is the length of the interval divided by n, and we're letting n go to infinity, so this term is becoming infinitesimally small. And in doing so, remember back on the video how letting the number n get larger and larger produces better and better approximations, and in the limit we recover the area under the curve. Here's the nice phrase to remember: limit of a Riemann sum. Beautiful. Now let's look at the notion of upper and lower sums. And we can easily determine whether a Riemann sum will produce an upper or a lower sum in special cases. So here's a special case, and here's a special case. Look at that again. Here's a special case. Here's a special case. Let's look at them side by side. So here are the two special cases. The picture on the left is dealing with a function which is decreasing over the interval a to b. The picture on the right is dealing with a function that is increasing over the interval a to b. The rectangles in both cases are protruding past the graph, giving overestimates. So, what can we do when a function is decreasing? We can use the arbitrary point as left endpoints and guarantee that our Riemann sum will be an overestimate or an upper sum. In the second picture, where the function is increasing, we can choose in our Riemann sum to use right endpoints to produce heights of rectangles and be guaranteed that we will produce an overestimate or an upper sum. All right, let's bring that together in one case that the function is increasing. Then choosing right endpoints produces an upper sum. Choosing left endpoints to produce heights produces a lower sum. All right, very nice. So here's an example where we're working with a function, f of x being x squared. This is just a parabola with vertex at the origin. So this parabola is a decreasing function when x's are negative, and an increasing function when x's are positive. Since the interval that we're interested in is x is positive, 2 to 4, then the function f will be an increasing function. Since f is increasing, if we use right endpoints, then the Riemann sum will be an overestimate or an upper sum. Again, as the function f is increasing on this interval 2 to 4, using left endpoints, we'll produce a Riemann sum, which is a lower sum. Let's go about producing that Riemann sum. We're provided with an n value of 4. Let's look at what the base of each rectangle will be. B minus a over n is 2 over 4, which is 1/2. So we have 1/2 times a height, 1/2 times a height, 1/2 times a height, and so forth. And then if we want to produce an upper sum, we're going to use right endpoints. For the interval 2 to 4, the very first right endpoint is 1/2 away from 2, or 2.5, otherwise written as 5/2. Evaluating the function, which is x squared, at 5 over 2 produces the height of the first rectangle, multiplied by 1/2, the base, produces the area of the first rectangle. Continue on with the second rectangle, which will have a height of f of 3. How did we get 3? By adding 1/2 to 5 over 2. Okay, very good. Then on the lower sum side, let's start with the very first term. The first rectangle is going to have a base of 1/2. What do we do for the height? We want to produce a lower sum. How can we produce a lower sum? Well, we're going to use left endpoints. Why? Because the function is an increasing function. So for this interval, 2 to 4, what's the very first left endpoint? Well, that's the left endpoint of the overall interval, 2. So we evaluate f at 2. Then the second left endpoint is adding 1/2 to 2 to get 5 over 2, and so forth. Excellent. All right. So here is an assignment, a little bit more involved than the example that we just did. Since we're using a function f to be the sine wave is periodic, it goes up and down. We're going to use as the interval, a to b, 0 to pi. Over that interval, the function sine will be both increasing and decreasing. Now, use that the area under the curve, sine of x, over this interval 0 to pi is exactly 2. Then compute left endpoint approximations, right endpoint approximations for n values 10, 50, and 100. And then using that the area under the curve is 2, compare these left and right endpoint approximations with 2 to determine which of these L10, R10, and so forth are upper sums and which are lower sums. Very nice. So that concludes section 1.1, Approximating Area. Thank you so much for watching. See you on the next one.